Hello everyone, hope you're doing and welcome back to my channel. I'm very happy to welcome all of you and your families. And coming to today's question, it's on the harder level, but I'm damn sure that if you have been following my videos, if you have been, revising or doing every question, then I'm damn sure that you will be able to solve this question. There are actually a sub problems here, which is related to another topic. If you're good in that topic, then I'm damn sure you will be finding it easy. Let's see how it works. Okay, we are at day 30 of the October daily Leetcode challenge, and this is the hard question. Minimum number of removals to make mountain array. Okay, so what is a mountain array? Basically, we'll get to know that, but see it here. The mountain array basically means that, okay, initially what will happen, there will be one element. Okay, to the left of that, all elements will be smaller than that, and similarly to the right, all elements will be smaller than that. Not just that, you have to see this condition also. So basically, yeah, you may recall that an array ARR is a mountain array if and only if, okay, the length of that is greater than 3. Why is this condition is there? I will tell you, because there is a need for it. I will tell you why it is so. Okay, before that, see it here. There exists some index I. Okay, let me call it as a peak from the starting itself, so that it becomes very easy for you to understand. Okay, because eventually you will realize that this is acting as a peak element, this particular I, but initially we will not be knowing that. Okay, so this particular I is basically a peak element. Okay, where I is not zero. That is, I cannot be the start element. Similarly, I cannot be the last element. Remember that this condition is very, very important. Okay. This will be edge case in your solution. Okay. I cannot, that is, a peak element can never be the first element. The peak element can never be the last element. Okay. Such that, okay, this particular condition exists. Okay. What is happening here? See here. Basically, if you see here, there is a sequence getting formed here such that all the elements are strictly greater than the previous elements. Okay. For example, the first element. Okay, let me start from here. That is, the ith element is greater than its previous element. Similarly, this element is greater than its previous element, strictly greater than its previous element. Similarly, follows till the first element. Okay, that is from the ith element. That's towards the left of the ith element. Okay, there is a sequence getting followed. What is the sequence? Every element is strictly greater than its previous element. Okay, as simple as that. Okay, the other thing is, see, this part was towards the left of the current peak element. Okay, now come to the right of the current peak element. What is happening? There is a totally opposite sequence getting followed. What is that? The ith element is strictly greater than its next element. Similarly, this next element is strictly greater than its next element, and so on till the last element. Okay, so if you see in example here, this is what is happening here. Okay, for example, 3 is the peak here. Then all the elements, that is 3, must be greater than its previous element. In this case, it is 2. Similarly, once I reach the peak, the sequence will change. What is that? Now 3 will be greater than its next element. Okay, this is how it is. Okay, that is how it works. Okay, yeah, but this is another example. What is, see here, the 6 is the peak. Okay, so what is happening? I am at 1, 5 is strictly greater than 1, then again 6 is strictly greater than 5. Okay, there is 1 sequence completed. I reach the peak. Now I have to fall from the peak. Okay, that is, I have to fall from the mountain. So how will that work? See, I'm at 6. The next element is strictly less than 6. Similarly, the next element is strictly less than 3. Okay, that is, I'm falling from the mountain. First, I will be climbing the mountain, and then I will be falling from the mountain. Okay, that is, we'll be reaching the peak first. Once we reach the peak, we'll be that is going down. Okay, we'll be coming down. As simple as that. That is the basic solution. So yeah, remember, they are strictly greater. They are asking, and now coming to why we need a length of greater than 3. Okay, see, as I mentioned, the peak cannot be the first element. Okay, similarly, peak cannot be the last element. Okay, in that case, that should be see, why 3 elements are required. Why 3 or more than 3 elements are required is that because there has to be at least one element which is smaller than my peak. Similarly, there has to be at least one element which is to the other side of my peak. That is, there has to be at least one element which is to the left of my peak. There has to be at least one element to the right of my peak. Okay, as simple as that. That is the basic idea. Okay, so given an array of nums, return the minimum number of elements to be removed. Okay, to make nums a mountain array. Okay, as simple as that. In this first example, you see it's already forming a mountain array. Okay, 3 is the peak, and the two ones, so it's left and right, are simply acting as element which is following this particular sequence. Okay, so here we don't have to remove anything, so answer is 0. Now coming to this particular thing, if you see here 6 is acting as a peak. Okay, so what are the things here? To reach 6, if you see here, there are some of the elements are breaking the sequence. Okay, in this case, this 2 and this particular one, they are breaking the sequence. Okay, if I remove them, I will get a pure rise. Okay, this is the rise. Okay, similarly, if you see here, certain elements are breaking the sequence here towards the right. Okay, so if I remove this particular 2, again I will get a sequence which is following a downfall. Okay, here is the downfall, and here is the rise. So we have to remove these 2 elements. Okay, here from the left of the peak, and we have to remove this element from the right of the peak. So total we have to remove 3 elements. Okay, as simple as that. If you talk about the constraints, okay, total length of the num is going to be from 3 till 1000. Okay, and this doesn't matter to us, actually, because it can be of any value. If you are using some other program language to solve it, then you have to bother, because but anyway, this is input, right? They would have chosen a proper data type in which this full values can be adjusted. Okay, as simple as that. It's guaranteed that you can make a mountain array out of num. This is very, very important. Otherwise, you have to think of a condition where if this is not, it's not possible, then what you have to return. Okay, in this case, it is guaranteed that the input can be made into a mountain array after certain removals. Okay, so what we have to return, we have to return the minimum number of elements that needs to be removed. Okay, so like why I was saying this particular problem can be broken down into sub problems, and those sub problems, if you are aware of certain concepts, you can get them. So what are those concepts? The first concept is the longest, okay, increasing subsequence. Okay, that is the first concept, longest increasing subsequence. What it means is that if I am given an array, how to find the longest increasing okay, let me show you through example first. Okay. For example, let us say this is the num set. Okay. I am trying to find the longest increasing subsequence. Okay. Then I will try to find the longest decreasing subsequence. Okay. Why is this important? Is because, see, the idea that I am going to follow is that, let us say this is the peak. So from the first element till the peak, okay, I will try to find what is the longest increasing subsequence and what is the length of that. That is the length of the longest increasing subsequence. Okay. Okay, that will tell me how many elements are in following the sequence. Okay, so I will take this particular number, how many elements are here, I will take that number. In this case, if there are 5 elements, then I will take the how many elements are following the longest increasing subsequence. Okay, that number I will subtract that two. Okay, that is the number of elements towards the left of the peak minus the number of elements in the longest increasing subsequence. Okay, that will tell me how many elements need to be removed from the left of the peak. Similarly, I will just do a same thing towards the right. Okay, I will find longest decreasing subsequence for this particular part. Okay, here the number of elements here, if you see, there are 4. Okay, so I have to find, I have to subtract, from 4 I need to subtract the length of the longest decreasing subsequence. Okay, that will tell me how many elements are falling in the sequence. If I subtract, that is 4 minus the longest decreasing subsequence length, that will tell me how many elements next need to be removed from the right of the peak. Okay, together, okay, that the number of elements that needs to be removed from the left of the peak plus the number of elements that needs to be removed from the right of the peak will tell me the total answer here. Okay, that's what I'm going to do. Before that, I'll just quickly do a dry run, show you how these things are calculated. Okay, I will take, okay, let me zoom in first. Yeah, so I will initialize them, all of them, with 1. Okay, the length will be same as that of the length of the given nums. Okay, then I will show you how the LIS, that is the longest increase subsequence, calculated. Okay, so first of all, we will start from the second element onwards. Okay, because see, increasing subsequence basically means how many elements to the prior that are following that sequence. Okay, so I'll start from 5. What I have to do, go to all the elements previous, that is all the elements which are left of it. Okay, and see how many of them satisfy the property that they should be less than 5. Okay, in this case there is only one element and obviously it is less than 5. Okay, so I have to take its value. Okay, take its value, add 1 to it and save it here. Okay, take its value, add 1 to it and save it here, so this becomes 2. Okay, now come to 3. So how many elements are towards the left of 3? There are 2 elements. Go to each of them and see which of them are less than 3. Okay, 5 is not less than 3, but yeah, 1 is less than 3. Okay, what you have to do, take the value, that is LIS value of 1, add 1 to it and store it here. It again becomes 2. So this forms an LIS array. Okay, longest increasing subsequence. Okay, that is, if I am at 5, what is going to be the longest increasing subsequence? Similarly, if I am at 3, what is going to be the longest increasing subsequence? Okay, which includes 3. Okay, similarly, when I'm at 5, what is the length of the longest increasing subsequence including 5? Okay, that is 2. Okay, that is the basic idea. Now coming to the longest decreasing subsequence, it's totally the opposite of what is increasing subsequence. Okay, here what I have to do is very simple. Okay, very simple. I will tell you the way exactly what I've done in my code. Okay, I will start from here, from right towards the left. In the first is what we did, from left towards the right, but here I will start from right towards the left and follow the same approach only. Okay, so I am at 3. First value will be as it is only. Okay, now I am at 5. So how many elements towards this right are less than current element? That is how 5 is there. How many elements are towards right? There is only one element. Okay, whether it is less than 5 or not, yeah, it is less than 5. So take its value. Okay, add 1 to it and store it here. Okay, it becomes 2. Okay, now come to 1. How many elements are towards the right? There are 2 elements towards the right. Okay, how many of them are less than 1? Obviously none of them are less than 1, so I can't do anything here. It will remain as it is only. Okay, this will tell me how many, that is the, if I am at current element, okay, including this particular element. Okay, what is the length of the longest decreasing subsequence including the current element? that will tell me that. Okay, so this is the length of the longest decreasing subsequence for the ith element. Okay, so if I'm at this particular element, ith element, start including it, what is the length of the longest decreasing subsequence? Okay, that is the basic idea. Okay, that is one, and this is the longest increasing subsequence. So this is how it is calculated. So I hope you understand my idea. What I'm going to do, I'm going to try to find the peak here. Okay, once I find the peak, what I'm doing, I'm going to do, find the length of the longest increasing subsequence. Okay, till this point. Okay, that is include the whole of the array towards the left of the peak and find the LIS for that. Okay, the LIS will be length, basically length of the longest increasing subsequence. Once I have that, okay, count how many elements I have here towards the left of the peak, subtract the length of the LIS. Okay, that will give me how many elements that needs to be removed from the left. Okay, then see this part. See this part here. I have to find the LDS. Okay, longest decreasing subsequence length. Okay, take that length. Okay, subtract it from how many elements are here towards the right of the peak. Okay, once I have that, okay, that will tell me how many elements that needs to be removed from the right. Okay, then I will add both, how many elements that needs to be removed from the left plus how many elements that needs to be removed from the right. That will give me this particular answer. Okay, we'll see that in calculation now. I hope you understood the basic what the problems I'm trying to solve. I have broken this question into two sub problems. One is LIS and one is LDS. Okay, once I have the LIS, that will longest increasing subsequence. I am good with the left part of the array. Okay, left part of the nums array. Okay, because I have the peak towards its left, I have to follow LIS. Okay, longest increasing subsequence. Why longest? Because see, that will allow me to remove the least possible element. Okay, remember the question is minimum number of elements to be removed. Okay, to get the minimum number of elements, I'm using the longest increasing subsequence. Okay, this will allow me to remove the minimum number of elements. Okay, in the left of the array. Similarly, when I'm at peak towards its right, I need to follow LDS, that is longest decreasing subsequence. Okay, that will allow me to remove the minimum number of elements towards its right. Okay, yeah, and one more thing which I mentioned in the starting itself, which will be edge case, is this one. Okay, the peak cannot be the first element. Similarly, the peak cannot be the last element. Okay, because see, peak basically means that towards its left something should be smaller than that. Similar towards its right something should be smaller than that. Okay, if it is a starting element, there is nothing left of it, right? So that's why peak cannot be in the starting and peak cannot be in the last element. As simple as that. That will form my edge case. So what I'm doing in my code, yeah, I'm simply taking a length of the current nums given to me. Then I'm, declaring array to find the LIS. Okay, I'm initializing all the values as one initially, and it will be of the length of the given nums. Okay, it will be also of length n. Okay, this will be for LIS. Okay, LIS is the longest increasing subsequence. Same thing I'm doing to find the LDS. Okay, what is LDS? Basically, the longest decreasing subsequence. Okay, LDS is same. I'm initializing all of them with one. Okay, it will be of the length n. Then I'm trying to calculate LIS. The same approach which I showed you in my example. Okay, this is in the diagram, whatever I showed you. This I can paste it in the comments also so that you can go through it once. Okay, the same thing I'm doing. Okay, start from the first element, go till the last element. Okay, yeah, one more thing that I want to tell you is that, see, since this thing, the peak cannot be the last element and it cannot be the first element. That is another reason why I am not calculating the LIS. That is, I don't want the LIS to end and the first element and the last element. Okay, that's why I am starting from the second element and I'm going till the second last element. Okay, I'm going till the second last element here. Okay, remember whatever value you give here, one less than that, it's where the actual follow will be lasting. Okay, it will be lasting till -2. Okay, so I'm starting from the second element and going till the second last element. As simple as that. What I have to do for each I, travel to all the elements over its left. Okay, that's what I'm doing in this loop. Okay, what is J? J is going to be J is going to take the value of all the elements towards its left of I. That's all the elements towards the left of I. Okay, one by one. So what I'm first of all checking whether nums of I is strictly greater than nums of J or not. Okay, that is the current value should be greater than each value of its left. Okay, if that's it only, then I'm going to do this particular condition here. Okay, see, I'm finding LIS, right, longest increasing subsequence. Whatever I showed you in the diagram, same thing I'm doing it here. Okay, if nums of I is greater than nums of J, what I have to do, take nums LDS of J. Okay, sorry, here, take LIS of J, add 1 to it. Okay, and store it in LIS of I. Okay, since LIS of I can already be having some value, so we have to include the max condition here. Okay, check if LIS of I, the previous value of LFI, is either greater than the current value that I'm going to populate. Whichever of them is largest, take that and populate it here. Okay, long is increasing subsequence of I. As simple as that. Then print LS of I. Same time I'm going to do for LDS. Okay, longest decreasing subsequence. Here the only thing is, see, see what I'm doing it here. Start from the right and go towards the left. Okay, if you do that, you have to follow the same code for LS. Whatever you followed, you have to follow the same code. But only thing is, you have to start in the other direction. Okay, then you will get the LDS. So I'm starting from the yeah. the second last element, and I am going till the first element. Remember, if I'm writing 0 here, I will be stopping at 1. Okay, so I'm starting from the second last element, going till the second element. Okay, in the reverse order. Okay, in the reverse order. Okay, what is j? J will be every element towards the right of I. Every element towards the right of I. Okay, same thing here. If nums of I is greater than nums of j, do the same thing. Okay, check if LDS of j plus 1 is greater than the current value of LDS of I. If it is so, take the max, whichever is the max, and update it in LDS of I and print it. Okay, this is just for your purpose. Now comes the most important part, which I did not show in the dry run. What's that? See, any number can be the peak except the first and the last element. Any number can be the peak. That's why I am going to try each element as the peak, and then I will try to find how many elements are getting removed out of that. Okay, but we'll have to take only the minimum number of elements. So whichever case gives us the minimum number of elements, we will take that and return as the answer. As simple as that. Okay, so what I'm doing yet? Yeah, start from the first element, go till the second last element. Okay, remember one thing, for each I, it can be peak. Remember, I is going to be the peak. Okay, I'm trying to make each I as the peak, and then I'm trying to find how many elements are need to be removed if that is the peak. Okay, that will give me idea of what are elements that needs to be removed. For each case, we'll try to find the number of elements that needs to be removed if I is the peak. Okay, then we'll try to see which particular I gives us the minimum number of elements to be removed. Okay, that is which particular peak gives us the minimum elements to be removed. Okay, but remember, there is a property of peak, that is, it there must be at least one element towards the left of it. There must be at least one element towards the right of it, which is smaller than that. Okay, I can be peak only if there is at least one element to its left, which is smaller. I can be peak only if there is at least one element towards the right, which is smaller than it. Okay, so what I'm going to check, LIS of I should be greater than 1. Similarly, LDs of I should be greater than 1. Only then this particular element can act as a peak. Okay, so what I'm trying to check it here, yeah, this is the number of elements that needs to be removed from the left of the peak, and this is the number of elements that needs to be removed from the right of the peak. Okay, how I'm doing that, see here, let me zoom in again. Yeah, so this is going to be the total number of elements towards the left of the peak, including the peak. Okay, for example, if you see here, let us take the index of 1. Okay, 0, 1 and 2. Okay, if I'm at index 2, okay, how many elements are here towards the left, including the peak? There will be 3 elements. Okay, 3 elements. So to the index 2, add 1. So we'll get a total number of elements, including the pink, towards its left. Okay, take that number. Okay, and subtract from it the LIS of I. That is the longest increase subsequence of I. That will tell me, this particular thing will tell me how many elements are not following the increasing subsequence. Okay, that those needs to be removed towards the left of the peak. Okay, now the same thing I'm going to do in the right of the peak. Okay, so how many elements are there in the right of the peak? This is the number of elements which are going to be there in the right of the peak. Okay, n minus I. Okay, remember, I'm okay, let us see the same thing here. Okay, suppose I am here. Okay, that is, I'm at index 1. How many elements are that were the right of this? It's going to be n, which is 3. 3 minus 1. Okay, there are two elements over the right of 3, including the peak. Okay, there are two elements. Same thing I'm doing it here. This is the total number of elements toward the right of the peak, including the peak. Okay, n minus I is the number of elements toward the right of the peak, including the peak. From that, what I'm subtracting, LDS of I. Okay, so this whole thing will give me total number of elements that needs to be removed from the right of the peak. This will tell me the number of elements that needs to be removed from the left of the peak. Add them to get the total number of elements that needs to be removed. Okay, remember, this is the element that needs to be removed when I is the peak. I will try to make every number as the peak and see how many elements are to be removed. Whichever is the lowest, I'm going to take that. So what I'm going to do, see, initially I started with n. Okay, initially my minimum element to be removed is n. Okay, this assumption. Okay, assumption. What I'm going to do next, I'm taking this, whether this is minimum compared to what I had previously. Okay, this is the answer, right? So I'm checking if this particular value, the value that I'm calculating currently, is smaller than the value that I had previously. If that is so, update the minimum element to remove. Okay, finally, once I come out of this particular for loop, okay, I will return this as the answer. Okay, this will be my final answer. Okay, let me quickly run this and show you. This particular video, I think, got slightly bigger, but I hope you understood, because see, this is marked as a hard question. I'm sure whenever you see a hard question, most of you who are beginners will be leaving the question thinking it's not worth spending time on. It's too hard. It will not be coming in interviews. But let me tell you this very frankly, this question I have seen in an interview. That's why I'm focusing too much on this, because see here. Here the concept LIS being taught. Okay, LIS, I'm damn sure if you are a CS student, you will be having this in your topics also, in your studies also, in your subject also. Okay, your data structure algorithm, it will be a subject, you will having this particular algorithm. Okay, LIS algorithm, longest increasing subsequence. You will be following a different approach to get that, but here I'm using this particular approach. Okay, to get it. Okay, yeah, as simple as that. So once I found LIS, I'm applying this towards the left of the current peak. For every peak, I'm applying this and trying to find how many elements are to be removed. Okay, Same thing, I'm calculating how many elements are removed in each case and which is the minimum. I'm taking that and I'm updating it here, and finally I'm returning it. So I have submitted the solution. As you can see, this is clearing all the test cases. Okay, the you will normally have two test cases. This third case I have additionally added it. So what here happening here is, if you see, these elements cannot be peak. Okay, these elements cannot be peak. Okay, because there is no element towards his left which is smaller than them. Okay, none of them can be peak. Okay, yeah, this much, none of them can be peak, because if you take any one of them as peak, you will not have anything towards his left which is smaller than them. Okay, that is why this cannot be peak. This is going to be the peak. Okay, the first peak and the last peak. Okay, that's why this will is going to be the peak. Okay, just pause this video and analyze why these particular elements cannot be the peak. I made this test case just for you to analyze. Okay, that is the reason why I was saying this, and this condition will help you in this case. Okay, this is where it is will be helping you. If you remove this condition, this particular test case will fail. Okay, this particular test case will fail. Okay, this cannot be peak because this does not have even a single element towards the left which is smaller than them. That is not a definition of peak. Peak should have at least one element which is smaller than them. Okay, that's why I've included that condition. Okay, take a screenshot of this, or you can make this test case. Okay, otherwise I will give you this nums in the comment section. You can add it as an additional test case and check your answer. Okay, yeah, so that's why this condition is important. Because the definition given here. Okay, the area of I should be at least greater than one element. Okay, that's what they're trying to say here. Okay, otherwise, see, mountain cannot be there. Like, if you imagine the mountain, right? There has to be a dip, then you will rise and again you will fall back. Okay, that is what is a mountain, right? Same thing here. If you are starting itself from the peak, then how it can be a mountain, right? It will not be a mountain then. So yeah, friend, that is all for today. This question I really liked it. That's why I'm spending this much time to make you understand. I'm not sure if I am succeeding in my, in my efforts to make the solution easier for you or not. But I'm damn sure that I've covered everything here. Okay, even if you're not able to understand in the first attempt, please pause this video, please rewind this video, or maybe at least see the content that I provided in the comment section. I'm damn sure it will be helping you, because see, I provided the comments also. These things will be definitely helping you. Only thing I'm doubtful is that whether you are aware of this particular concept or not, longest increasing subsequence. If you're aware of that, I'm damn sure you will be understanding my solution. If you're not aware, please go back, do some homework, try to learn what is this, and then come back again. Okay, because see, here we are using this to solve the question. Okay, so if you're not aware of this, then I'm damn sure it will be a hard question for you. But if you're aware of this, this will be it will never be a hard question for you. I'm damn sure this will not be a hard question then. Okay, so yeah, friend, that was all for today. I've already solved this question. This solution actually works. I will give you the same in the comment section. You can try this out. If you like my efforts, please do subscribe to my channel. It really gives a lot of motivation to continue further. Okay. See you tomorrow. Thanks a lot, and happy Diwali to all of you once again.